All right, let's go over the Unit 6 review for chapters 8 and 9. This is covering the z intervals, the one proportion and two proportion, and the z tests, one proportion and two proportion. It's a big unit. It's going to be a bigger test. So let's go through these free response questions, make sure we know how to interpret everything. Write everything down on the PDF. Make sure you submit that into the Canvas assignment so you can get credit for it. And please go back and review the slideshow that I'm going over if you need to for additional support, or ask me for help if you need it. All right, let's begin. Make sure you have your paper to write on, either the printed off version of this or just a clean sheet of paper so you can write your work, and a TI-84 calculator. You can use your TI-84 calculator app on your Chromebook, or you can have your own TI-84 calculator to work out these problems. Here we go. Number 1, Hornets player Devonte Graham practices his free throws constantly at practice. A simple random sample from the season's practices shows that Graham made 39 of 50 free throw attempts. Construct and interpret a 95% confidence interval for the proportion of free throws Graham makes for the season. So let's start with the interpret the 95% confidence level. Okay, you have a template. So part of the extra credit assignment is 8 templates that you can go through, and you can use those to help you not only answer these questions, but you can get extra points too for doing them if you do the flashcards. So the confidence level template is in repeated sampling of about whatever percent your confidence level set at of all intervals calculated will capture the true parameter in context. So think about how you want to write that. Pause it if you want to try writing it on your own. And once you unpause, you can check the next slide. So the way I said this was, in repeated sampling of size 50, approximately 95% of confidence intervals created will capture the true proportion of free throws Graham makes for the season at practice. If you need to adjust your answer, then go ahead and do that now. All right, the next part. State the parameter of interest in the procedure you wish to carry out. Well, we're looking for a proportion. So our goal is to figure out a one proportion z interval, since we are trying to estimate that proportion. So the P would be the true proportion of free throws Devonte Graham makes at this practice for the season. And we want to do a one sample z interval for P, and it's a one proportion z interval in your calculator. Let's state and check the appropriate conditions. Remember, that's the assumptions and conditions. So remember, we need random, independent, and large counts. Those are the 3 things that we're looking for here. Random, independent, or 10%, and large counts. So let's look at the random. We have a simple random sample. It says so right here. So that checks off. 10%. While there were 50 free throw attempts, we can assume, we hope that that's less than 10% of the free throw shot. But if not, these are independent shots, so we should be all right in this situation. So 10% is met. Large counts. N times the proportion. We don't have the true proportion, so we use the sample proportion. NP is greater than or equal to 10, and N1 minus P is greater than or equal to 10. Well, there were 39 free throw attempts that got made. So that's 39 in your success column, which means there's going to be 11 in your non-success column. So those are both at least 10. So we're good. We've met the large counts conditions, the independent, and the random. Now we're ready to do the interval. So I write the formula, set it up, but I do all my work in the calculator. So if you know how to use that, see if you can construct it first, and pause the video, and then you can check the next slide. So the formula is going to be p hat plus or minus z star square root p hat 1 minus p hat over n. That's the standard error formula. The z star, remember, we can get from table B. In your formula sheet, you'll get a link to your formula sheet. At the very bottom of table B, it has that infinity sign, and it'll give you your confidence level. So you just look at the row next to it, pick out your confidence level. 95% is 1.96. But you do all that, you throw the stuff in the formula. You can actually do all the work in your calculator from there. So we will go into your stat tests, and you go to option A, Locate that now so you make sure you can get these numbers. One prop Z interval. You're going to input your 39 out of 50. That's your proportion. Your confidence level here is 95%. So we want to put that as 0.95. Then we're going to go down and calculate it. You get an interval of 0.66518 to 0.89482. So we write that interval down. And all we need to really say is, we set up the formula. We can say using technology, we obtained this interval. Write this formula down and then actually crunch the numbers using your calculator. So we have to summarize it. So we interpret it. So we say we are using this template, blank confident that the interval from blank to blank captures the true parameter in context. So again, you have that template for confidence intervals. We are 95% confident the interval from our numbers that we calculated, 0.66518 to 0.89482, captures the true proportion of free throws Graham makes for this season at practice. So the true proportion is your parameter. You're trying to capture that. And that's a 1 proportion Z interval. On to question 2. Okay, question 2 has a few parts. Do younger people use Twitter more often than older people? In a random sample of 316 teenage internet users, 53% used Twitter. In a separate random sample of 532 adult internet users, 44% used Twitter. So there's a difference. Construct and interpret a 90% confidence interval for the difference between the proportions of teenage and adult internet users who use Twitter. And then we want to know, does the interval give convincing evidence of a difference between the population proportions? Explain. And what would happen to your interval if you if you kept everything the same but increase your confidence level to 99%? So we want to address these 3 questions. The first one's going to be the longest one because that's going to be the constructing the interval. So that would normally count for more points in a free response question. So we start with the pass program on these. We want to say, we identify your parameter in context. So the parameter is it's a 2-sample Z interval for PT minus PA. Well, what is that? PT is the true difference in proportion of teenage and adult, so the T for teenage, A for adult, internet users who use Twitter. So we're trying to see that difference. And when we do a point estimate, we do that sample, we have 53% and 44%. So if we subtract those two, we get 9%. So teenage minus adults is 0.09. That's our point estimate. And we want to check our conditions. So the assumptions is what that A stands for. Assumptions and conditions. We assume these things have to work out. So is it a random sample? Usually it is. Are we less than 10% or 1/10 of all internet users for teens and adults? Obviously. And do your large counts. So you're 53% for teens and you're 44% for adults. Remember, this is not a test. This is an interval. So we don't assume they're the same. So we use those different sample proportions to get your large count. So 167, 149, 234, 298, all greater than or equal to 10. So now we can do our work. Let me clear these off. So here's this formula for that. Now, you're not going to work all that out by hand, but the formula is the difference in the estimates plus or minus Z star, and you do your different proportions, P 1 minus P over N, P 1 minus P over N, but this one's for teens, this one's for adults. Plug all that in, and if you do it by hand, you'd get that. I don't do it by hand. I go to your stat menu, go down to option B, 2 prop Z interval. And then you're going to, you're going to run that interval by putting your large counts in. 167 is what you get when you multiply 53% times 316. Now I had to round it because if you actually look at my calculator here, I'll show you. Hold on. Let me pause this for a second. Sorry about that. So if you look at my calculator, if you multiply 53% by 316.53 times 316, you actually have 167.48. We can't do anything with the decimal, so we got to round that to the nearest number. So I just said 167, and then if you do the complement of that, 0.47 times 316, you get 148.52 or 149. So you'll see that in my large counts, I basically are, let me represent that. When I plug those in, I just round to 167. And similar for the other one, I just did 44%, 0.44 times 532, and I got around 234, so I rounded it. It's not gonna be perfect. But when you run that test or that interval, your sample proportions are gonna be slightly different because, again, these are not exactly 53%. This is 0.528. And this is not exactly 44%, it's 0.439, but it's so close that it's going to give you a similar number anyway. See that difference there? 0.03044 versus 0.14683. They're all about between 3% and 15%. So you're good. And then you summarize it saying we're 90% confident the interval from 0.0318 to 0.1482 captures the true difference in proportion of teenage and adult internet users who use Twitter. Now, a word of caution. I know you're so ingrained in probably remembering 1.96, but if it's a different confidence level, so we have a 90% confidence level here, that's going to change this. And remember, you're going to go to table B to get that. So don't assume it's going to be 1.96. You have to look at your confidence level and get that number for your Z-star. So on to the next part of the question. We want to explain, does your interval give convincing evidence of a difference between the population proportions? Well, this is not a test, but we can still identify if something's convincing, whether or not a number is in your interval. So remember, your interval is from about 0.03 to 0.146. Well, that tells me there's a difference because 0 would be no difference. 0 is not included in that interval. So you can basically say, yeah, there's a difference. The interval does not include 0, indicates no difference. There's enough evidence of a difference in proportion. So yeah, that is convincing evidence from a statistical point of view, even though it's not a test. What would happen if you increase the confidence level? Well, that increases the Z-star. That makes the margin of error wider. So when it's all said and done, it's going to be a wider interval. Margin of error increases. So that's question 2. Again, I encourage you to pause through each part, try them on your own first, and you can check them, okay? That's going to help you understand it better. All right, the next 2 questions are dealing with tests. So the first one is going to be probably a 1 proportion Z-test. So let's look at the question. A random sample of 800 items produced on a new machine showed that 31 of them are defective. The factory will get rid of the machine if the data indicates that the proportion of defective items is significantly more than 3%. So we assume it's 3%, but we're trying to prove that it's more. At a significance level of 5%, does the factory get rid of the machine or not? Let's find out. Our parameter, well, that would be the true proportion of defective items produced on the new machine. Your statistic is the p-hat, 31 out of 800. It's 0.03875. So it is more than 3%, but it's statistically enough to warrant replacing the machine. So the hypotheses would be HO, P equals 0.03. Remember, P is always equal to on the null, and HA, P is greater than 0.03. So since it's more, we do a 1 proportion Z-test, 1 sample Z-test for P. All right, the next part we want to do our assumptions and conditions. Remember, random, independent, normal. So let's check them. Was it a random sample? Yes, we could just say that. 10%, okay, 800 is less than 10% of all items produced by machine. We just state that. We assume that. That's all we can do. Large counts. Don't use p-hat, use p. Remember, we're assume the null is true in a test. So 800 times 0.03, 800 times 0.97, both greater than or equal to 10. And our alpha level was given to us, it's 5%, so we write that. All right, so now we do all the statistical work, and I use the calculator, but the formula is z equals p hat minus p over the square root p1 minus p over n. Remember, that's your standard deviation with the null as your p. That p is, the null is 0.03. That statistic was 0.03875. If we plug in the proportion there, you get about 1.45. This says to draw a picture of it. So if you were to draw a picture, standard normal curve with z as your mean, that z-score 1.45 or greater. The probability of getting that is your p-value. Again, the probability of getting a z of 1.45 or greater is your p-value in this case. Now I don't go through all that process. Again, I run the test. You don't have to write the formula down. You can simply run the test, state that you use technology, and report your z and your p. So you go to one prop z-test because it's a one proportion. This is a greater than, so input your null is 0.03. Your x is 31 out of 800. That was your given information. And it's a greater than. And we go down to calculate. And we get the following items. We get z equals 1.45. P is 0.0734. You get your p hat and your n, which you don't need to report because you already have those. And that is the number that we need to summarize with. So once you get your p value, you just name z, p, name the test, say you did z, p, you got to use technology to get those, and you summarize. So the summary, remember we have a template. In this case, p is greater than alpha, so we fail to reject the null. There's not sufficient evidence to conclude, and then the alternative in context of the problem. So see if you can write your summary, pause it, and then check it with me. Okay, so the summary, because 0.0735 is greater than a equals 0.05, we fail to reject the null. We don't have convincing evidence to support the claim that the true proportion of defective items produced on the new machine is more than 3%. So the factory is going to keep the machine. So the next question is, based on your conclusion, what type of error would you have just made? Well, let's look at those two errors. We got type 1 and type 2. Turns out a type 2 error is when you fail to reject the null when it's actually false. Since we failed to reject the null, that's the kind of error we could make in this problem if we did make an error. So what does that look like? Well, a type 2 error, since we failed to reject the null, it's possible the null was false. It's possible the null was false. Now, we're not saying it is, but it's possible the null was false. So in this case, the machine would actually be producing defective items, but we didn't say that they should replace it. So it's going to keep producing defective items. That's a consequence, right? That could be a problem. So identifying a consequence from an error is one of the things you would have to do in on a free response question on your exam. And finally, question number 4. 2 types of hives are being tested to determine if there's a difference in the percentage of adult patient reactions. Not beehives, but like hives that appear in your skin. 15 out of a random sample of 100 adults given medication A still had hives 30 minutes after taking the medication. Only 30 out of another random sample of 120 adults given medication B still had hives 30 minutes after taking the medication. Remember, this is an experiment, so you want to have control over this so they have the same amount of time. Do the data provide convincing evidence of a difference in the proportion of adult patients' reactions for the types of medications at the alpha equals 0.10 level? So that alpha level is 10%. So the probability of making a type 1 error is higher, remember? So let's interpret the p, then we have to interpret the p-value. We'll do that last. So first, we state our parameter, hypotheses. In this case, the proportion of A minus PAB with the difference proportion of adult patient reactions for medications A and B. They were just labeled A and B because that's what they're called. The sample would be P hat A minus P hat B, 15 out of 100 minus 30 out of 120. 0.15 minus 0.25, which is negative 0.10. So you could go either way. It doesn't matter if you did the B minus A. I just typically use the first one minus the second one. So the null would be that there is no difference, so that's equal to 0. The alternative, now this is where we got to be very careful. Do the data provide convincing evidence of a difference? It doesn't say more, doesn't say less, it just says difference. And when you see that, that's a not equal. So that's where you have to look very carefully in kind of those last sentences of the problem to see what your alternative should be. Not equal, it's a two-sided test. So you're going on one and the other side of that normal curve. So it's a two-sample z-test, two-proportion z-test for PA minus PB. What do we do? Well, first, I buck all the rules and I run the test in my calculator. I wanna know all the counts and all the values and whatnot. So when you do your calculations, go into your calculator and try see if you can emulate this. Stat tests 6, 2 prop z test. I put my first as 15 out of 100, and then 30 out of 120, and I ran the not equals because it's a two-sided test. Now, if you go down to calculate, you'll get all the numbers we need. You'll get your z-score, you'll get your p-value, your sample proportions, and your pool proportion. Remember this number down here? That's your PC. And that's what we use to do our large counts. So we need that, 0.2045, 454545. And our sample size is 100 and 120. But if you go down to do the draw, it'll give you a picture too. So it kind of gives you an idea of what's going on here, right? It's the probability of being more extreme than what you see, but since it's a two-sided test, it's in either direction. So we do since our z-score is negative, one of those calculations is less than or equal to negative 1.83, but the other one is greater than or equal to positive 1.83, since it could go the other way too. So it's doubling your p-value when you do that work. So doing our random independent, random 10% large counts, just remember that when you're working that out, your random sample, just state it. 10%, write something in context. So 10% of all adults taking medication A, 10% of all adults take medication B. I'll list that out. And then and we know that because of the amount of the sample, 100. These are a lot of medications, people taking these medications. So we assume these tests are representative. And then we use that same PC. So you can get that PC that the calculator had by adding your numerators divided by the sum of your denominators. But we can also just get it from the calculator. And then remember, these two add to 1, these two add to 1. And your large counts are going to be they're all going to be greater than or equal to 10, as you can see there. So we say the sampling distribution is approximately normal. So we've actually run the test already. We have the numbers. We can write down the formula. So if you look over here, that's what the answer key that I got this from looks like. But again, that formula, not necessary to write down. You really just need your Z and your P. You can run the two proportion Z tests in your calculator. Using the draw option will actually get you that picture if you need to draw a picture. And all that's required is you to state the test, state that you use technology, and you report your Z and your p-value. That's really all you gotta do. So this part right here, that's kind of extra. I'm not taking off points if you don't include that, but I do need you to name the test and report your Z and P from your calculator. All right, so what do we do from there? We have to summarize, right? So let's do that. So remember, the p-value here, it's less than alpha. Our alpha is 10%. So in this case, we reject the null. There's sufficient evidence to conclude. So you have a template here. Now we go through and we do the following. We say because 0.0671 is less than alpha at 10%, we reject the null. We do have sufficient evidence to support the claim that the true difference in proportion of adult patient reactions for med A and B is different, not equal. So we have evidence to conclude it's different, not less than, not greater than, just different. That's the two-sided test. Now let's interpret the p-value. Again, there's a template for that. So here's the template. If assuming the null is true in context, the probability of attainment results at least as extreme as the sample is, whatever the p-value is. Or your template, see if you can write out your interpretation and check it with me now. Okay, if there is no difference, assume the null, in patient reactions for medication A and B, the probability of obtaining results at least as extreme as the sample is 0.0672. That's your p-value, folks. And guys, that's the end of the review. I hope that you take some time to go back and look at the other lessons. Make sure you do the practice chapter 9 test in sapling. I've gone over that in class with you, but you can try it in sapling too to get some extra practice. And then your test will be in your next class period. Thank you for watching. Bye-bye.